Start on time. So, dear distinguished speakers, ladies and gentlemen, college and students, good afternoon. Thank you for coming and welcome you all to this technology forum. It is my pleasure to chair this forum on the topic of advanced manufacturing today. So, probably manufacturing is a forever topic in science and technology in the world today. Over the past decades, manufacturing has become a driving force to the rapid development of economy in China and the world. So the question is whether China or Greater China region can still maintain its leading position in manufacturing. So answer this question will more or less be related to whether we can further advance manufacturing technology in all aspects. So today, we are very, very happy to invite the 5 renowned speakers with us today. They will share us their view on manufacturing and exchange their research outcome in areas including material science engineering, automation, robotics, industrial engineering, and biomedical engineering and device. So first of all, let me introduce the 5 distinguished speakers first. Professor Mai Wing. Professor Mai is the University Chair and Professor of Mechanical Engineering, the University of Sydney, Australia. The second external speaker is Professor Kazuhiro Kosugi. Professor Kazuki currently is a professor of the Department of Bioengineering and Robotics, Graduate School of Engineering, Tohoku University, Japan. Now let me introduce 3 internal speakers. Professor Gary Feng. Professor Feng right now is a chair professor and associate provost. Okay. In the department, he's a chair professor of mechatronic engineering in the Department of Mechanical Biomedical Engineering, CityU. The second internal speaker is Professor Cui Guoliang. Professor Cui is the head and chair professor of industrial engineering, Department of System Engineering and Engineering Management, CityU. The last internal speaker is Professor Li Wenjun. Professor Li is a chair professor of biomedical engineering, Department of Mechanical and Biomedical Engineering, CityU. So we will have all speakers to give presentation first, and then followed by question and answer session. Professor Mai. So now let's move to the second speaker, Professor Gary Feng. And Professor Feng is going to present the topic, cooperative control of multi-agent system. Professor Feng has been in CityU since 2000, where he is now a chair professor of mechatronic engineering. So Professor Feng and I are long-term collaborators. We're personally also good friends for many years. Okay. So Professor Feng was a Changjiang chair professor, awarded by Ministry of Education China. He was a senior lecturer at the School of Electrical Engineering, University of New South Wales, Australia, before he joined CityU. He was awarded the Humboldt Fellowship in 1997, and he got the IEEE Transaction Outstanding Paper Award. He has co-authored over 250 international journals, among which over 100 are in IEEE transaction. It's an amazing number, actually. Yeah. His current research interest includes intelligent system and control, network system and control, and multi-agent system and control. Professor Feng is an IEEE fellow and editor board members for many top journals, including IEEE Transaction on Automatic Control. That's a very top journal in control area. Also IEEE Transaction on Father System. Okay, now let's welcome Professor Feng.
Okay. Good afternoon, everyone. First, I would like to take this opportunity to thank Professor Sun for his nice introduction. And it's true, we joined the CityU almost the same time. And since then, we have collaborated a lot in various research projects and a number of the publications. What I'm going to show today, actually, the experiments I'm going to show in the end of this presentation actually was done by his student. So, as you know, today's topic is about manufacturing. So automation is one of the key technologies for manufacturing. So what I'm going to discuss particularly is about the cooperative control of multi-agent system. For example, the robot systems. If you look at the outline of my talk, we're going to introduce some application of the multi-agent system first, and some major approaches to cooperative control of multi-agent systems, and then the main challenge in this particular area. And after that, I'm going to focus on one particular approach. We call it event-triggered cooperative control of multi-agent systems. And of course, we'll show you some simulation example and experiment in the end before we come to the conclusions. So first, I'd like to introduce the application of the multi-agent systems. As you know, the many engineering systems can be described by the multi-agent system. I just mentioned the multi-robot system, sensor networks, and many other things. So the second thing, the multi-agent system can be used to describe collective behaviors of biological groups. For example, I mentioned two examples here. This is a flock of the birds. So it's a beautiful picture here, and also this colony of the ants. So that's a typical examples of collective behavior of the biological systems or groups. The key elements of the multi-agent system, actually you use three keywords to describe them. The first one, for each agent, it has dynamics. And for the group, it has topologies, a communication among the agents. Finally, we need to have some kind of control. In the engineering field, normally we use the distributed control. So that's what I'm going to talk today. And as I mentioned in the applications, lots of the engineering system can be described by multi-agent system. For example, there's the formations of the UAV, unmanned aerial vehicles, or robot system network. So that's a typical example of multi-agent systems. To describe the formation of such a system, we can use like one keyword. In this case, problem formulation can be classified as a consensus. The second example is in surveillance, like for the forest. If you want to monitor the fire situation in the forest, that's a key important, very important critical issue for the forest protection. So cooperative control of heterogeneous multi-agent system can be used to describe this kind of situation. As I just mentioned, for forest protection, so that's a sensor networks. To describe such a system or for problem formulation, we can call it a cooperative output regulation. So to summarize application of the cooperative control, we can describe them like a bird flocking and a formation like a robots and a rendezvous. And actually is one particular examples. We look at it. And those kind of problems can be, in general, described by consensus. In the consensus, we have two kinds of consensus. One is the leaderless consensus, one is the leader-following consensus. So, of course, in different situations, you have a different scenario. And from different angle, we call it a state consensus. In other words, all the states converge to the same value. That's called the state consensus. Of course, if we look at the output of the system, it's an output consensus. So allow one to describe a similar problem, but using a different technique. We call it cooperative output regulation. I'm going to show this consensus and the cooperative output regulation today. Now, let's summarize what's the most popular approaches recently in those areas. The early consensus protocols can be described either by continuous approach. It's a very simple, there's some connection matrix coefficients of the network, and that's just a difference between the state of the labeling agents. We're using that as a feedback, as a control to drive all the agents to the same state value. That's the same state value. This early approach is continuous approach. And of course, you can also use a periodical sampling approach. Sometimes we call it discrete time approaches. So you basically just at the sampling time, you use a control signal. And the third class of the control approaches is called the event-triggered approach. That's a focus where I'm going to talk today. So basically, what's this difference between this sampling, this periodical sampling, here is not a periodical, is sampling only happens when it's necessary. Otherwise, in general, you don't need to sample the signals. Only necessary to guarantee either stability or performance. Then we can sample your signals. From the approach point of view, we can have the number of approaches. First one we call the internal reference model approaches. One particular paper proved that the internal reference model is both necessary and sufficient condition for output consensus, for heterogeneous multi-agent systems. Another kind of approaches is called the cooperative output regulation approaches. This kind of approach is based on the output regulation methods, which is for single system. Basically, this kind of approach developed by my friend, actually, Jie Huang and his collaborators during the last few years. Of course, in order to deal with some kind of uncertainty or to reduce the knowledge of a requirement of the prior information of communication network, we can use adaptive control approaches. So many different approaches. The major one, actually I listed them here. And the major techniques to use to study of the multi-agent system actually can be classified as Lyapunov function approaches or algebra graph theory and switching system theory. That's a major approach in this particular area. So what's the main challenge currently in this area? I summarize some of them. Firstly, the most existing results only deal with very simple dynamics, like the first order, one integrator, a double integrator, and some like a very simple linear system, okay? So this is a typical model they use for local agent. But for more general agent dynamics, for example, very general linear system or non-linear system, that's lots of challenge there. And also, if most of works have the assumption all the local agents have the same dynamics, so it's sometimes called a homogeneous agent system. So how to deal with heterogeneous? In other words, all the dynamics in different agents are different. So how to deal with them? That's also the challenge. And the third one is normally the communication between your agents is bandwidth is limited. And also the onboard energy source is very limited. How to deal with those finite communication bandwidths and limited the onboard energy? So that's a third problem. It's a challenge as well. And also because in practice, all the agents are subject to various uncertainties or disturbance. How to deal with them? So that's also the challenge. And finally, not the least, there's a communication constraint of networks. Because you have the networks, communication network among the agents, because of that communication networks, the your robot is moving around, the topology can be time varying. So how to deal with time varying topologies? That's a challenge. And how to deal with packet dropouts. You know that because of communication nowadays is mobile, so some signal or some packet could be dropped during the transmission. So therefore, how to deal with those packet dropouts? And the third one, the time delays. Because of communication needs time. How to deal with those time delays in the communication networks. So all those are challenges. Unfortunately, we cannot deal with all of them. But what I'm going to do today to deal with actually we're going to discuss the heterogeneous multi-agent system, but if we talk only linear system, we also deal with this one, the finite communication bandwidth and limited onboard energy. So that's the focus we're going to talk today. To deal with this one, we introduced the so-called event-triggered cooperative control of multi-agent systems. Some motivation. So why we need to use the event-triggered control? As I mentioned, the individual agent, especially for that small or very simple, like a sensor network, the sensors are very simple one. So the individual agents only equipped with microprocessors and some simple actuation modules with very limited onboard energy sources, normally the battery, right? In order to keep your system operating as long as possible, you want to reduce the energy consumption as much as possible, right? So that's the objective. So basically, in order to achieve that, we can use the event-triggered control. The key idea of event-triggered control is to reduce communication load. It has been shown that for the agent, the most element or most activity one agent consumes their energy is the communication. So therefore, if we can reduce the communication load, we should be able to save a lot of energy. The traditional control, as I just mentioned, is a continuous control or periodic sampling, right? So you design your control based on those series. But for event-triggered strategy, the communication and the control update is only triggered when it's necessary, when needed. So then, this kind of approach is not proposed by us, right? This approach actually was proposed for stabilizing problem for single system in 2007 by this person. And actually, before that, someone showed that the traditional periodic sampling is not as good as the event-triggered control strategy for the stochastic system by Ostrom and his colleagues. And in the past few years, the many works applied to the multi-agent system with very simple agent dynamics. That's an example about 2012, and this also an example of 2013. This is my student, myself, we wrote the paper on this topic about 2013. This is published in one of the best journals in the control. Two of them. One is Justin Dongsun, Professor Sun mentioned, IEEE transaction or automatic control. It's one of them. The second one is Automatica. We published the paper in the Automatica. It's two best control journals. Okay, now in order to develop the event-triggered control, we needed to define a few things. First, we need to define problem measurement and measurement error. The one in our approaches, we're using the combined measurement that we define our measurement as this, basically the difference between the state variables. And we define the measurement error as this one, the difference of that particular event happening time, TIK. And that's a difference. So the most important thing for the event-triggered control is to define or design proper triggering condition. So the one question you may ask, what kind of mechanism, what kind of the theory you should rely on to design this one? Actually, this proper triggering condition should be designed in such a way that to guarantee stability of the closed loop system, or performance. It's up to your designer to choose. But in our case, we only consider the stability in this work. Now, next, I'm going to show the approaches what we developed for the heterogeneous multi-agent systems. As I mentioned, the internal reference model, we have two kinds of approaches. One, if you have an actual system, and sometimes we call the neither. If you have the neither following, we can look at this system. If you don't have a neither, we can have this one, we call it the neither-less consensus. Neither-less consensus. We can look at the system in the two levels. We look at this table first. So basically, this is different agents, right? We call it the heterogeneous system. So that's why the dynamics are different. But we have the connection here, means they have communication among those neighboring agents. And this is the dynamics of each agent are different. Okay, we only talk about a linear system. The key idea in that we call this higher level, this upper level, actually is that, look at this. The upper level is that we're using the same dynamics. This one is what we designed. We call it an internal reference. We design our reference model such that in the upper level, all the reference models for all the agents approach each other. In other words, all the reference model achieve consensus first. And then each agent just need to follow their reference. Then we can achieve the consensus for whole system. That's the basic idea. And similarly, if you have an ecosystem, then we have an ecosystem here, and we design the internal reference model in such a way all the internal reference model nodes follow that ecosystem, and then we design this controller further such that each agent to follow that reference model. Then we can achieve the consensus for whole system. That's the basic idea. It looks very simple, but how to achieve that, how to prove that stability, how to prove the consensus is a different story. But as I said, I'm not going to discuss the detail of proof, but I'm going to show you the idea. The idea is, look at this one. Let's look at, as I said before, we look at this, how to make sure the internal reference model approach each other. So this one is a homogeneous system, right? This is the dynamics the same, S the dynamics the same. So what we are going to do, we first look at the same dynamics, and we objective to achieve the consensus for all these states. And we choose a controller. This is the event-triggered controller. And then this K is defined by this one and satisfy this the so-called extended Descartes equations. We have the results as follows. Under this assumption, this is a standard assumption for controller problem. Normally, AB is stabilizable or it's controllable, and the G is connected. You have to make sure your connection, the communication graph is connected. If it's connected, it's not connected, you cannot achieve consensus. So that's a very basic assumption. Under these two assumptions, we can show that with such a triggering condition, with some parameters given here, we can make sure the consensus problem can be solved for the homogeneous system, okay, for the homogeneous system. That's, of course, the proof is very complex, but I'll not jump here. And then we look at the heterogeneous system. In this case, based on the results of homogeneous, so look at this dynamic system, we try to achieve output consensus in this case, and we design the dynamic output fit controller, and look at it here. This is, look at it here. This is your all internal reference model with the same dynamics, okay? So basically, for the homogeneous system, this is the part. So this is the event-triggered control. Of course, this is a control signal, this is a control UI, and this one just like our observer, because we talk about output feedback. So this is just like an observer, very simple observer. And based on this dynamic output feedback controller, suppose we choose a similar control gain and satisfy this Descartes equation, then we can have the seminal results. The problem for heterogeneous multi-agent system consensus problem can be solved if we choose this event triggering condition. And if and only if that's both necessary and sufficient condition of these two sets of equations can be satisfied. So that's a very theoretical work, but the idea is very simple. And then we are going to show some output regulation of the heterogeneous multi-agent system. Remember, in the previous case, we not consider any disturbance. But here, we are going to consider the disturbance. And also, at the same time, we consider some reference signal as well. So we assume the disturbance and the references can be described by this, we call it axial system. As I just mentioned, just like a needle. In this case, what we're trying to do, we're trying to make sure all the agents, all the agents will track this reference signal in the axial system. That's the objective. So summarizing the objective is make sure the whole closed loop system is asymptotically stable, and all the errors, okay, all the errors goes to zero. So that's a problem. And using the similar idea I just presented, we can show with such an output feedback controller, this is very similar to the I just mentioned for homogeneous internal reference model. With such a controller, and this one also similar to the observer, with such a controller, then with such a Descartes equation, we can guarantee under such assumptions, then we can find the solution for the problem. We can find the solution for the problem. So that's basically, this trigger condition is more complex, okay? Because the problem described is more complex. So with such a trigger condition, with such a measurement and a measurement error, we can solve the problem of cooperative output regulation for the concerned system, Now, because we talk about the event trigger, it's a kind of switching signal, okay? Your system switching on, switching off. So in order to make sure your system is really working, we need to deal with two issues. We call it the feasibility analysis. To have to exclude two phenomena. The first phenomena is called the signal triggering. We talk about event triggering. You have to trigger from time to time. Only one trigger is not the event trigger system. So therefore, we want to avoid only triggering once. Okay? So after that triggering, it's no more triggering. So we want to exclude such a phenomenon. We can prove that, actually. In this theorem, we showed that with triggering condition 2.3, 2.9 previously, we can show no agent will exhibit singular triggering behavior. So in other words, such a problem can be avoided with such a controller. And the second problem that's also very tricky in practice, we call it a Zener behavior. What that means, in the finite time of period, you have infinite number of triggering. So in other words, you are switching between the event, it's become zero. So it's switching very, very fast, infinity fast. So this one will not be tolerated in practice. So in practice, we have to avoid that one. So what we can show, the two consecutive triggering time difference will be strictly positive. Actually, we can show that in this theorem with the same triggering condition. We can show that no agent will exhibit Zener behavior. So that's a good results for this approach. And you can, I didn't mention that the one problem with such approach actually is a drawback of event trigger condition such like this. You have to continuously monitor those measurements and the state variables. So in other words, you have to continuous checking condition. Somehow you can save some kind of the communication cost, but there's still lots of communication among the agents. To really address this problem, we propose this so-called self-triggered strategy. The idea of this one, we can show a next triggering time is estimated based on information at the previous triggering time. In other words, with such a triggering mechanism, there's no continuous monitoring, no continuous triggering condition. So you can really save a lot of communication costs. So actually, we propose this new triggering condition. This new triggering condition, look at it, only depends on triggering time. Okay, it's not continuous time anymore. What we can show, of course, the details, I'm not going to skip it, but the result is this. With such a self-triggering rule, we can still guarantee the consensus problem can be solved. Consensus problem can be solved. So this theorem 6, actually for theorem 7, we can show for this kind of self-triggering mechanism, it's no singular triggering or no Zener behavior. So in other words, feasibility study can be guaranteed as well, Okay, it's a bit boring, right, all the theorems, but the idea is very simple. We just try to use the triggering condition to replace continuous or periodic sampling to save energy. Basically, this is the key idea, to save energy. And now, next, I'm going to show you some examples. This is a very simple example. This is an example come from this particular paper. It's actually a virtual spacecraft. So its dynamics can be described by this. And the communication graph is 1, 2, 3, 4, 5. Means they have the communication among them. And we can ask, after some state transformation, we can rewrite the dynamics of this system into this format. Basically, this is a typical heterogeneous linear system, okay? So our control objective is to make sure all the states approach each other and the velocity approach each other, same velocity and same states. So this is the basic idea. Equivalently, in the time, in the state space, just all the xi goes to xj. So that's the state consensus, basically state consensus problem in this particular example. Now, using our approaches, we can design the controller. In the simulation, we end up with such a result. So basically, all the arrows, the state arrow goes to there, for all the agents. And also their velocities all goes to the same velocity, So that's a typical example of the one particular practical example. And the second one, as I just mentioned before I started this presentation, this work was done by the Professor Sun students. So actually, Professor Sun has done a lot in the robot formation control. So what I'm showing here is one example. So basically, that's all the number of the robots, 5 robots, try to formulate the circle. So that's a process. As I just mentioned, that's a work done by the Professor Sun and his team. The formation control is can be classified or can be transformed into the consensus problem. So that's a result. Basically, all the robots will circulate around the central point here. Okay. Okay, finally, the conclusions. In this particular talk, I just present some view of some most recent advances in the cooperative control of multi-agent systems. And in particular, we propose some event-triggered, self-triggered control schemes. This particular schemes to deal with the homogeneous multi-agent system consensus and the heterogeneous multi-agent system output consensus. At the same time, we also present some cooperative output regulation of the multi-agent system. Actually, this work was done by one of our students. Actually, this work has been submitted to the automatic, and so it's still under review. And finally, we also analyze some feasibility of proposed control approaches. Basically, that feasibility study shows that those schemes should be working in practice. Finally, thank you very much. Thank you for your time, and thank you.
Thank you, Professor Feng. Our third speaker, Professor Kosugi, is going to present the topic, learning from real issues to a new generation of industrial robots. Maybe, Professor, you can set up the computer while I introduce you. Professor Kosugi currently is a professor in the Department of Bioengineering and Robotics at the Tohoku University, Japan. Professor Kosugi is a good friend of our department of CityU because he regularly visits our department. He also is the academic advisor for our robotics and automation center. I started to know Professor Kosugi nearly 20 years ago. I remember in 1995 when I went to Nagoya to attend the conference. Professor Kosugi is the organizing chair of that very great conference. I was very impressed by his actively organizing the great conference. And I start to pay attention to Professor Kosugi's work is mainly because one piece of his research, very similar to mine, or to my research, we talk about the coordination of multi-robot coordination. Over the past 20 years, I have seen very successful paths of Professor Kosugi. Let me briefly introduce you. He received the JSME Awards for the best paper from the Japan Society of Mechanical Engineers in 2002 and 2005. The RSJ Award for the best paper from the Robotics Society of Japan in 2005. He's an IEEE Fellow, a JSME Fellow, a ICE Fellow, and RSI Fellow. So many fellowships. He was the president of the IEEE Robotics and Automation Society for 2010 to 2011. He's currently the IEEE Division 10 Director-elect for 2014. Now let's welcome Professor Kosugi.
Thank you very much. Thank you very much for your kind introduction, and thank you very much for your invitation to this very important a forum. And today I'd like to talk about toward the next generation of industrial robots. I took the title of Advanced something manufacturing seriously, so different from my usual topic. I'd like to talk about industrial robots. Okay, I hope it will be interesting for you. This is I just want to start with this slide. In 1946. ENIAC, the world's first electric digital computer, was unveiled. Okay? This year is a very important year for industrial robots because at the same time, George Devol developed the magnetic controller playback device for factory automation. In 1954, this George designed a programmable robot for universal automation, and its patent was granted in 1961. In 1956, Unimation, originated from the original was Universal Automation, now abbreviated as Unimation. The company Unimation was established by Joe Engelberger. Okay, and this is our first industrial robot. Started to be sold in 1961. And actually, this is a patent submitted by the George and granted in 1961. Okay, programmed article transfer. Now, as you know, a lot of industrial robots are utilized in our factories. So, let me explain the current situation of industrial robots. Okay, we have a lot of demands for the industrial robots. Like you may remember that Foxconn or Honhai, as a president, announced that they'd like to introduce 1 million robots to their factories in order to replace the kind of human labor. But they couldn't. Why couldn't we increase the number of working industrial robots? And usually people say that because we do not have enough number of systems integrators, SIers, okay? Is this really true? So would like to raise a question for this ordinary answers, okay? I just believe that because today's industrial robots technology is not developed enough to handle the demands. That is a kind of my starting point of this talk. So what kind of issues do we have for the industrial robots? As you may know, or you may not know, when we'd like to utilize the industrial robots, we have to design an end effector or a robot hand and a jig or a fixture and a parts feeder, for example, for each task, okay? And usually it takes a lot of time and especially the peripheral systems used for a robot system often exceeds the cost of a robot. In some sense, it's very strange, but this is true. This is a true story. And actually, industrial robot is a multidimensional programmable positioning system with high positioning repeatability. Okay? Usually, the motion of the industrial robot is programmed by the teaching operation. And also, and when we'd like to design we'd like to utilize the industrial robot, we have to design the end effector for each object so that the geometric relation between the object held by this end effector and the robot is known precisely. So in the current industrial robot, by designing in the end effector for each object, we could assume that the robot knows the position and orientation of the handled object precisely. At the same time, when we suppose that we'd like to do some assembly task, we need a jig or fixture. And the jig or fixture is designed for each object so that the geometric relation between the robot and the object supported by the jig is known precisely. Okay? Based on these two assumptions, based on the precise relations among the robot and the object held by the end effector and the object supported by the fixture or jig, the motion of the object held by the end effector relative to the object supported by the jig is precisely controlled, and thus the assembly is carried out by controlling the motion of the robot. Okay, as you can see in the current situation, actually current industrial robots are not so universal as we could imagine. Okay, and actually the customization and the programming of a robot requires a lot of man hours and the cost is very high. So I think that we'd like to propose one solution for these issues. Okay. And actually, we need a robot which executes tasks without using an end effector specifically designed for each task, which means that we need a multi-purpose robot hands which could handle various objects such as parts and tools. And also, since, the end effector, if we utilize a general purpose robot hand, a multi-purpose robot hands, then that we are not sure the about the geometric relation between the object and the robot motion is not, we don't know, we are not sure where the object is. So visual information, we need visual information to identify the geometric relation between the object held by the multi-purpose robot hand and the hand itself, our robot. Also, in order to execute the tasks without using a jig specifically designed for each task, the object should be fixed by the robot arm. So which means that we need two arms in coordination. And also, we need, because since we don't have any information a priori, manipulation of an object based on the visual information have to be done. We don't want to utilize the parts feeder, for example. Then the beam picking using a multi-purpose robot hand is very important. Okay. So for this purpose, we have developed several systems. So I'd like to introduce. I think this is the first time for me to introduce this system in this country. First one, we consider the existing robot gripper. Okay, usually end effector. Suppose that we'd like to grasp something, then we usually utilize just a single degree freedom gripper. And so we decided to reconsider the finger shapes. We introduced three concepts: caging, and self-alignment, and form closure. Caging is like this one, okay? By designing the fingertip shape appropriately, we can capture the object inside, even if something happens, some unnecessary impact happens, is applied to this object. At this moment, we are just talking about a circular object. Okay? Then, by designing the fingertip appropriately, you can see that the self-alignment is possible. And after that, form closure is guaranteed and to support the object family. Okay, this is one example. Okay, now the guy is roughly positioning the parts. And this is a very simple gripper, single degree freedom. But you can see that, based on the concept, it can robustly grasp the object and put it in the appropriate place. Okay, this is very simple, but it works. And so, at the same time, you can picking different small parts, as shown here. I prepared a lot of slides so that I can entertain you. This is a ball. This is a gear. This is a single, very simple gripper, right? But by optimizing the finger shape, we can do that. Actually, the optimization is carried out based on the, so as to maximize the radius range of the grasped object by this gripper. Okay. And now I'd like to go to another types of a robot hand. In the production system, sometimes we'd like to grasp a very small parts. Sometimes we'd like to grasp a hand, tool, okay? In our case, we do that. So we design a very simple gripper, which is actuated by only two motors, okay? And you will see what's going to happen. It can grasp a thin plate, okay? and a circular object, and a tool. This is the electric driver. So by utilizing this very simple, one hand, you can grasp several types of object. And we can also install the sensor at the end of the fingers, okay? Like by implementing a force sensor, you can see that left-hand side is metal fingers. This is a sensor integrated fingers. By feedbacking, feedback the pressure to apply to the each finger, we can do that. Okay. Also, okay, we can also implement a suction cup simultaneously. Then you can handle such a thin card, and you can put a thin card, a kind of personal card, into a plastic bag. Good. This is very simple. Okay. As I mentioned, we also need a dual-arm coordination. Okay. So we redesigned the existing dual-arm system, control system. We can do that. The hands is the same hand as before. Okay. Sorry, this is not a dance pattern robot. Okay. Now, okay, now it can change the configuration. It changed the configuration of the fingers, and it can squeeze this printer. And could put it into the box. Okay, you can see that how such a simple robot hand can manipulate can grasp the object as well as can squeeze the larger object. Okay. Then let me explain the next one. Manipulation of a multipurpose robot hand using visual information. Okay, visual tracking part is, we did this experiments project in cooperation with Professor Koichi Hashimoto in our university. He's a specialist of visual tracking. So I'm a specialist of manipulation. This is a kind of a combination of our system. So now you can see that they put a vision system identifies this box. And now the system has to localize where the plastic bag is. Okay. As in the case of a previous case, they can open the bag by using the suction force. People complain that still the motion is very slow. Actually, we can increase the speed of the manipulators, but at this moment we don't want to destroy our system. That is why kind of motion is a little bit relatively slow. Okay. Okay. Next one is I'm going to show you one example, taking out a part from this plastic bag. Okay. First, the vision system localize this plastic bag as well as where the parts is located inside of the bag, and then now it grasps. Okay. And then the two arms coordination is carried out. And bring this plastic bag into the cutter. Okay. So by utilizing the visual information, we can handle various objects by utilizing a general purpose robot hand. Then I would like to show you another one is bean picking. This is actually many people are trying to realize this picking, bean picking. But in this case, this scene is very cluttered, and it's not so easy to identify where the parts is. And actually, this is carried out using by single camera. And so, in this case, the depth information is not so precise. So we utilize the previous optimum shape gripper, having optimized fingertip shape, and then we can do that. At the same time, the system, identifies and measures the length of the bolt, and the short one is put here, and the longer one is put here. We have demonstrated this one in the previous IREX International Robotic Exhibition held last year in Tokyo, and this is from that demonstration. This was a challenge from a visual information side, and also a challenge from the control point of view. Okay, this is old, well-known topics, but still unsolved. Okay, and then I would like to sometimes, suppose that we would like to assemble parts. Okay, then in that case, we also have to concerned with if we don't know exactly where the part is, we couldn't assemble it. But we need the visual information. At the same time, we have to control the motion of each part, relative to the external force applied to the part, appropriately, so to avoid jamming. At the same time, let's say, absorb the motion errors. So this is a combination of a visual servo and impedance servo with a monocular vision system. Again, this is the case with a monocular vision system. Okay. And by utilizing the recent results, we can also, this is just only for the visual servo part. By utilizing a stereo vision system, we can also increase the response and accuracy of the visual tracking. And you can see that later, this is a bit, slippage between the finger and this object is artificially created. But because this is controlled based on the visual information, it can automatically, adjust the slippage between the object and the part. And okay, this is suppose that we'd like to assembly some part to here. Okay, in that case, if I held the object like this, it have to be it have to be stiff along this direction. But if it has a slippage, and in order to do the same motion, we have to. So in some sense, force control coordinate system have to be attached to the manipulated object. Okay. Real example will be shown later, but you can see that even if the slippage between the object and the fingers are artificially given, the system can can handle it. The original impedance characteristics is attached to the manipulated object. Okay, and by using that, we can assemble two parts by using multi-purpose robot hands and based on the visual and the impedance information. Okay. Eventually, it turns out that this could be also utilized for teaching. Teaching by showing. Now, this guy, is showing that what he wants these two parts assembled. Okay, how these two parts are assembled. Later, you are going to see a more interesting example. Now, these are different types of general purpose, multi-purpose robot hands, and okay. Now that assembly is carried out based on the force information as well as the visual information. Okay. I think the next one is more interesting. Okay. And this time, reference state is given, of course, by this, by showing the result of the assembly this time, and okay, the peg is not completely inserted to this another part. Then, based on the information shown to this system, these two manipulators are going to assemble the parts as shown by the, as demonstrated by this guy. Okay. So, as a conclusion, as I mentioned, a programmable transfer machine or an industrial robot was invented for the universal automation. But unfortunately, today's automation, industrial robots are not so universal, considering today's real needs from the industries. To make the robots more universal, we have proposed multi-purpose robot hands, manipulation using the multi-purpose robot hands based on visual information, and assembly of two parts using the multi-fingered robot hands based on the visual information and the visual and the impedance servo. Okay, thank you very much for your kind attention. Thank you very much.
Thank you. Thank you, Professor Kosugi. So our next speaker is Professor Ko Cui. And Professor Cui is going to present the topic, A Quality Journey from Manufacturing to Field Operation with PHM. Professor Ko Cui right now is a head and the chair professor in the Department of System Engineering and Engineering Management. So Professor Cui is one of my very respected colleagues in CityU, not because he's leading our sister department, it's mainly because he's a significant contribution to industrial engineering, especially in statistics and data mining. So Professor Cui has been professor, associate professor in the School of Industrial and System Engineering at Georgia Tech from in 1990 to 2011. And research staff in the Quality Assurance Center and AT&T Bell in 1986 to 1990s. He received his PhD degree in statistics from the University of Wisconsin and Madison. Professor Choi is a fellow of the American Statistics Association, American Society of Quality, International Society for Engineering Asset Management, and many others. He received the NSF Young Investigator Award many years ago. Currently, Professor Choi is leading a big CRF project and also actively involved in SIM-based research project, mainly in health informatics. Now, let's welcome Professor Choi.
Okay, thank you for Professor Xundong, such a nice introduction, and more importantly, for putting up this section together. And I don't know about you, that I myself already learned a lot from several talks, the earlier talks, and I am a lifelong self-learner. I always enjoy learning, so that's why I got very excited from the earlier talks. And some of them, I could imagine that there could be collaborative opportunities there. And also, you could tell that, in fact, it was very interesting, right? You start with a more practical talk, and then a more mathematical talk, and then finally, it's really how the robots are working. So they are very different, but they are interrelated, okay? Like what Gary's talk was talking about that. A lot of the algorithm and theories he developed will be useful for this robotic technology. The same thing, actually, for the talk I'm going to talk about and the area I'm in, which is the industrial and system engineering. A lot of them are like that. We do system, okay, integration, collaboration, and optimization, and all that. And the same to the talk I'm going to talk about. In fact, when Professor Sun started inviting me to give a talk in this section, I had a little hesitation, because actually my latest work, or what I'm going to talk about, are not directly related to advanced manufacturing in the direct sense, but it's more, in a broader sense, it is related to the advanced manufacturing, the way I define it. But I accepted the invitation is because mainly that I see that things are really coming much closer together. In the old days, you could separate the manufacturing, the field operation and everything, the design and all that. As time goes on, everything is interrelated, okay? And things have become much closer to each other, and there are a lot of room for collaboration, and you can make much better impact if you integrate different expertise together, okay? So, and that's basically what I will start with is really, what I'm going to talk about is that, as Professor Sun introduced, I started my career in the Quality Assurance Center in Bell Labs. That's where a lot of quality methods started. At that time I was in Bell Labs, most quality methods were applied to manufacturing. Okay, we have all this at that time was really advanced manufacturing, because it's in a telecommunication company where they have all this semiconductor, all this, the highest level of advanced manufacturing, where they have a very high standard. That's why they need very high quality, and they need sophisticated methods to push for that quality standard. And similarly, in the old days, a lot of tools in industrial and system engineering, such as optimization, operational research, and other stochastic modeling methods. In the early time in industrial engineering, they were all developed in manufacturing application. They try to optimize the performance of manufacturing systems, okay? But as time changes, those methods, we have done a very good job in improving, okay, or optimizing manufacturing system. And as time goes on, there are a lot more other areas of application that those methods can be useful, okay? So that's the same as the type of technical tools I use are basically statistical methods based, Okay, the same thing. We started the methods in manufacturing. Now it goes beyond manufacturing, although it's still in the sense that it's linked with manufacturing. Okay, so what I'm going to do is that I start with some of the old tools which are very popular and very important in 20 or 30 years ago in manufacturing. Just give you some simple historical background. Then from there, I'll get into the main topic, which is the area is called prognostic and system health management, and which is a very popular area in these days by integrating. It's an integrated or interdisciplinary area where integrated statistical methods, a lot of quantitative modeling with the manufacturing problem as well as the field operation optimization. So I'll introduce that. Then I have a couple examples to illustrate, and a simple example as well as some more sophisticated examples we are currently working on. And finally, I would also try to relate it to some other application in human health in addition to what we call the system health. And I have to say that, as I said, I mean, when I started my career, one of the technical methods in statistics is called Taguchi method. That's where I started my research, and even during my PhD study, and after that, when I worked in Bell Lab, there was a time when Taguchi came from Japan to US and made a huge impact in terms of introducing the new method called Taguchi method, okay, to the American industry. Mainly in the electronic industry, automobile industry, those are the most competitive industry, which has made a huge impact in US. They started from Japan, brought it in US, in other parts of the world, and finally they make a big, huge impact in terms of improving the quality of the product processes. And that's where I started with. And I won't get into the detail of that. I just want to make one point here that even back then, okay, so a lot of old things, and doesn't mean that, I mean, they are still useful if you really understand what they are. In the old days, this is how Taguchi defined quality. You see how broad he defined it, okay? He defined that ideal quality means every product delivers the target performance each time it's used under all intended operating conditions throughout intended life with no harmful side effects. So these are very important concepts which continue to be useful and important even in advanced manufacturing. Okay, I just picked the last bullet point. He introduced this concept about no harmful side effect. Okay, so this was 30-something years ago. Nowadays, there's a concept called social responsibility. Okay, it becomes very popular now, but that was the idea introduced back then. Social laws. He defined something called quality laws. Okay, so good concept is always useful. It depends on when it's going to come up. Okay, and so that's one of the important concepts that make a huge impact in manufacturing. And also he kind of introduced this quality loss function. Instead of what we call this 0-1 loss, introduced what we call the quadratic loss, which also make a huge impact for statisticians and other quality experts to try to improve quality by quantifying, okay, that impact and performance improvement. And again, this is an illustration why and how a quality loss will help improve the products. And again, I won't have time to get into the detail of that. And this is just a list of the tools during the 20 or 30 years ago when this quality journey was really popular among all advanced manufacturing in US, including electronics, automobiles, telecommunications. Okay, so these are the popular tools, including reliability, design of experiments, statistical process control, and sampling inspection. So those are the 4 most popular technical tools related to statistical methods were being used and taught and being implemented in most manufacturing plants. Okay, and as I said, they have done a very good job. They were able to significantly improve the quality of the products. Now if you look at the automobiles during the 80s, the American cars We bought the American cars, you will have problem in 3 months, in a year, okay? When we bought a Japanese car, then it lasts for many years without problem. This was 30 years ago. Now, after 30 years, they were closing the gap by applying all this method. I mean, including the big three, Ford, Chrysler, and General Motors. So they are closing the gap. On the other hand, the Koreans are also catching up. So now we see that the quality gap is much smaller among these manufacturing products. Okay? The latest example, actually, you look at the cell phone, the same thing. Because in terms of applying the quality control and quality improvement in manufacturing, they have done a very good job. The gap is much smaller comparing to 30 years ago. Okay? So there's not as much room for the impact, for making impact. They're doing really well. Instead, now, all of a sudden, the similar type of tools can be very useful in other applications, in a broad sense in manufacturing. Okay? I call that a production quality to operation quality, okay? Because when we look at manufacturing nowadays, it's not just you sell the product, that's the end of it. It's about how well the customer feel about the product after they buy it. The same for automobile, the same for the cell phone you have. You want to see how well it lasts, okay? The reliability, the sustainability, and how convenient it is, and how user-friendly, and all that. Okay, so that is the focus, shifting from that quality, the beginning, the initial quality of the product, to how long the quality of the product will last, and what is the performance of that over the remaining, the lifetime of the product. So that's the focus is on now. So because in the same time the advancement of the technology, it is very feasible to apply similar type of tools from statistics into the application in the field operation of the product lifetime. And in the old days, we called it reliability, but the reliability itself is really limited sense. Now it's a lot broader sense about, okay, we don't even call it reliability now. We call it prognosis and system health management. Okay, it's really about how do you predict the condition of the product over the lifetime of the product, okay? Such that you could make intelligent decision, okay? How to improve, how to optimize various things. So that is the idea behind it. This idea was around quite a long time ago, but it was not popularly implemented because of the limitation of the technology. But the last 10 years or so, because the advancement of technology, it became very much feasible. Okay, it has a lot of application in different fields. And mainly it's really the advancement we're talking about. One has been around for a long, long time, is about computation. But more importantly, in terms of the hardware, it's really about data collection. Okay, the sensor, okay, we call it electronic data collection, became much more advanced and sophisticated, but more importantly, it became much less expensive. It makes it possible for any type of application. Before, you could afford putting 1 or 2 sensors. Now you could afford putting 10, 20, or 100 sensors, okay, into any product you're manufacturing. So that make it feasible for the users, for the company, okay, to optimize the performance over the lifetime. Okay? At the same time, in addition to the sensoring, and the modeling method also has been advanced. Okay, in the old days, a lot of time you could only do very high level, or you need a lot of data, and you could only do what we call population modeling. You could do a models for the whole population of product. And nowadays, you could do modeling for each individual product because of the availability of more data and accuracy of the data, as well as the new developed sophisticated modeling method. All this make it possible. So if I summarize the tools for this PHM, it's a prognostic and system health management, it's still very much similar. Okay, the first 3 are the same names, except the emphasis are different. Okay, reliability, statistical process control, design experiment are the same 3 names. The emphasis are a little different. Okay, reliability now, In the old days, they look at the system reliability. Okay, they do some calculation, they design a system, they calculate for some reliability. And now the reliability shifts, okay, to more data-driven, okay, something called condition-based maintenance is really actually related to what Professor Gary Feng had just mentioned earlier, the event trigger, okay, model he's talking about, which is the same idea. In the old days, maintenance, you do routine maintenance over time, okay? And nowadays, because of the availability of information, sensor-based information, what you do, you want to save cost, okay, or resource, you will do what we call condition-based. If you know the condition of the part, for each individual part, you will have a different maintenance schedule for that. So this is how you kind of save and optimize the performance in system. The process control in the old days is really about manufacturing process. Now, the same method could be applied, we call anomaly detection. In the old days, you have very simple characteristics, and now you have a lot more data, okay? You are monitoring, because you have, remember we have so much sensor, so many different sensors you put in the system. You can monitor a lot of data, so that you combine the data together, you could trigger if something goes wrong. So the problem, basic problem is the same. The tools and the sophistication have significantly increased and improved. Design experiment the same way. We used to design simple experiment in the lab. If you could afford it, you could design simple experiment in the production line. And now you could actually design experiment in the field, okay? And how do you actually control it? How you decided what data you should be collecting. Okay, because as I said, there's so many different sensors. How many sensors do you need? Where do you put the sensor? Okay, those become new problems. And at the end, of course, the data mining comes in, and as the advancement of the data mining algorithms, a lot of this method involves a lot more variables, much larger quantity of data. You need data mining algorithms for doing the modeling part. So that is really how things are moving. Now, again, I mean, the general name, the name of the general field is called prognostic and system health management, but there are other names related to that. You may have heard of the engineering asset management, and there's other names, okay? But again, many of these fields, they share similar tools, similar ways of solving the problems. So what I'm going to do is I give you some motivation about what is it and why, okay, and how that we could use that. As I mentioned, the general method can be applicable to many, many different systems, okay? It can be manufacturing system, could be transportation system, energy system, as small as a cell phone or as big as a highway system, okay? And you could even extend it to what we call a human system, okay, which I will talk about at the end. And here are just some examples of different systems here. The point we want to emphasize here is that why do you want to monitor system and monitor the health of the system? The main reason why you want to monitor the health is if you really know well about the health condition of the system, you will react early enough before some disasters or something happen that will cost a significant amount of resources, could be financial, could be even human lives, okay? So the example will be if you consider an airplane as a system. So black box is the best example. People have been monitoring, okay, the data, the flight data over time when you're flying an airplane, okay? Except in the old days, you are monitoring it offline, okay? You are having a black box, remember? You're collecting all this data. When the accident happened, you retrieve your black box to find out what has gone wrong. Nowadays, of course, you can imagine technology will allow you to monitor the black box live, okay, or in real time. Then you may ask, why are they not doing it? In fact, they were talking about doing it after the Malaysian Airlines, right? But of course, it all goes back to the cost of it. The technology allows it all happen. It's a matter of cost now. So that goes beyond, it's related to us, but it goes beyond, could be a political or some other concern, okay? So that was the idea. If you really monitor, you have the black box monitor, you have the black box monitoring in real time, you could avoid certain accidents and all of that, okay? So that was the whole idea behind this. It's very feasible, very possible, okay? Same thing for others. So the cost of not reacting is really tremendous. That's why you want to do this health monitoring. More examples, power breakdown, you could think of what is the consequences. A lot more, right? Could be murder, could be all kind of problems, okay? Accidents and all of that. So it's a lot more. If you could avoid it, you could do something before that happens, that you're significantly safe. Okay, so one more motivation for this thing, that the methods in particular are very useful for complex systems. Why is that? The best example is Toyota. Okay, in fact, when I talk about this Toyota example, it's very interesting. In fact, it wasn't my example. I borrowed it from a colleague, some of our former colleagues. And if you remember, several years back, Toyota had a lot of braking problem in the automobiles. Okay, it creates a lot of problem, especially create a lot of news in U.S. It was a big deal. Okay, even myself, I started worrying. All the cars I bought in U.S. are Japanese, Toyota, okay? But now after that, I start thinking about, the latest one I bought is Hyundai, by the way, the first Korean car I bought. But because of Toyota braking problem, and people were wondering, Toyota is such a good company, why weren't they able to find out the reason? And some people told me this was the reason, okay? Because the system is getting very complex now. In the old days, automobiles are mainly mechanical, okay, mostly mechanical. Nowadays, automobiles, there are a lot of electronic components. So electronic components are a lot more complex. So when the accident happened, you bring it back to the shop, you could not reproduce it, okay? Because actually the failure events happens very rarely, okay? It's one in multi-millions times. So when you bring it back, you have to run it a million times to reproduce it. You can reproduce it, okay? And that's why if they cannot reproduce it, they cannot fix the problem. That was one of the explanations, although other people may not agree. But that explains why, how do we solve? So this actually generally called that rare event, very intermittent, and NFF refers to no fault find. It's the terminology they use that means that when the accident or the fraud took place in the field, when you bring it back to the shop, you could not repeat it. That's what we call no fault find, which is very common in electronic products now. Because electronic products have very high reliability. They have a very low failure rate. But when it happens, it could be very bad. Okay, so that's why you still have to deal with it. So how do you solve the problem? The way to solve the problem is really to take advantage of the sensor. If you know where to put the sensor, you could get the data when the accident takes place. So when you bring it back to the shop, you look at the data you have collected when the accident happened. Then you could find out what has gone wrong, you could fix it. Now, it's easy to say this. It's very difficult to do because there's so many different possibilities that failure could happen. Where do you put your sensor and what kind of data you collect, just like the black box. It's easy to say, it's hard to do. But at least there's a hope that if you take the right data and you're able to find out why, and you could fix it. Okay, so that is really the idea behind all this. This is just general definition of that, and I won't repeat it here. And these are some of the objectives. Again, the idea is really, by applying the approach, you could eliminate this, what we call unexpected and scheduled downtime. Okay? And also, you could develop the technology for what we call a self-cognizant electronic system. If you really understand when and how it happened, you could actually build up some self-correction algorithm to fix it. Okay, more data about this low fault find in particular. This is already old data. Okay, the new data even have a higher percentage. You look at the old data, Boeing, because Boeing, the airplane is very complex. So the no fault find percentage is very high. So that if they put more sensor, they could help significantly improve how they solve finding out the problem. and a lot more examples I won't have time to get into. Okay, so with all that, this slide actually I already explained before why. I explained earlier that it's because of advancement of technology, so I will not repeat it here. And just to scan through that, the data collection sensor technology, I already make the point that really the data we are getting now, they are more accurate, okay, a lot more quantity. So then that's why we could do a lot more. These are just examples. And the type of data, including RFID, which is getting very popular. Again, it's both the technology improvement, advancement, as well as the decrease of the cost. That's also very important. Until the cost goes down to a certain level, you could apply it in a broader sense. So you can have all kinds of sensors, all kinds of applications. These are just a few examples. So finally, I want to go through a few examples. It sounds very good, very great. How does it work? So I start with a simple bearing example. It's a very old example. This data set was collected at Georgia Tech. My colleague did all this, so I kind of borrowed his data set. And now he started with this old bearing problem. Now he's collecting data in the airplane engine now. So it goes from bearing to airplane engine. So it's a big jump. And so this is really the equipment he used. And he basically tried to collect data, the vibration, put a vibration sensor next to in the right place of a bearing, try to see how the vibration signal changes as the bearing deteriorates. So that's the whole idea. It's not a new, completely new problem. It's a very simple example to illustrate why the method will work. So these are the data he's collecting. So every 0.1 second, he has all this vibration signal. Then he will basically summarize the vibration signal. Then he will collect the data over time. Okay, he collect it every day, maybe 2 times a day or 1 time a day. See how the signal changes. Of course, there's a huge amount of data, right? Every 0.1 second, you have this already a huge functional data. So there are a lot of data modeling here, which I won't get into the detail. So he basically summarized the whole curve, vibration curve, into 7 points, take average of this 7 points. Then he plot the average of the 7 points over real time, first day, second day. So he see these changes, and then he start applying. So he, based on engineering knowledge, when this signal hits certain threshold, then that is an indication of a failure of the system. This is called a soft failure. Okay, so that is the simple idea behind it. So he will apply some parametric modeling to estimate this. So he has multiple curves like this. Okay, then you have to model both how the curve changes, you capture the trend. You also have to model the variation within each curve, as well as the variation from each part, each curve, because you have multiple curves. Every part could behave differently. So those are the statistical modeling involved. Okay? So these are the examples. Then they ran an experiment of 25, a bearing, then have 25 of these curves. So we do all this modeling. So finally, when you try to monitor a new bearing, then at the beginning, you use the model you fit to predict the remaining life of this bearing at the beginning. As time goes on, you collect new data of this new bearing, then you combine the new data with the old data, try to update the prediction of the remaining useful life. So because every bearing may behave differently, by combining the historical data with the new updated data, you could do better in prediction and performance. Okay, so that is the basic idea. So this is just some typical. Now, there are a lot of challenging research here, such as why are they taking average of the 7 points, that they make use of the information, but there may be other data, because again, you have functional data and all that. So here, there are other alternatives other than taking average of the 7 points. You could look at other features, summarize this curve. And once you have many of these features, there's a challenging question is that what are the features that affect the failure of the part? So those are a lot of challenging research there. And so these are some of the papers we have conducted. So we have what we call a simulator, machinery fault simulator here, that we could run experiments, simulate all kind of different faults, such as a crack, okay, such as losing tooth of the bearing or gearbox. So we could run our experiments, try to understand how we could model the data, how we could accurately predict the health condition of the part. So that's one area. The other exciting area we are getting into, there are plenty more other examples, but the other application we are getting into is called rechargeable battery. This is a very hot area, as you could tell that because of the energy and the environment, motivation. The electrical vehicle battery are becoming very popular, as well as many other electronic devices, such as your cell phone. So what we are doing here is that we try to investigate the degradation of a rechargeable battery, okay? And so we have the basic problem involves two types of problems. One is called state of health problem. One is called state of charge, okay? State of health problem is just like the battery. You understand the life or degradation curve of the battery. You want to predict how much more life of a battery. That means that, remember when you start using your cell phone, your battery will last for 3 days. Next week, next month, lasts 2.5 days. 2 years later, only lasts for 1 day. So that's the life of your cell phone. So that we do the same thing. We will study the curve to tell you when you should replace your battery, okay? State of charge refers to during every cycle of use. That is, your cell phone battery, you look at how many bars you have remaining in each time you use it. So that is called an estimation problem. You estimate accurately how much remaining battery in each cycle. Okay, those are two different problems. One is about degradation, okay, life degradation problem. The other one is really about a simple estimation problem. Both of them are very challenging, okay? So we have done a lot more in SOH study, the state of health study. Again, I don't have time to get into the detail, but we ran experiment, okay? There's a lot of issues here. We've identified, just like earlier. We have to identify the average of 7 points or the feature. The same way here. We have to take advantage, combine the knowledge about battery, the physics, the electronics. What is the best performance measure we could use, okay, to model that? And then all kind of issues. It's about user condition. Because everybody uses the battery differently. Like your electric vehicle, some people drive in the highway all the time, other people drive city. So we want to come up with the best model to predict the life of your electric vehicle battery. So that's very important. Okay, so we ran experiment. We have all kind of sophisticated modeling, which I have no time to get into the detail, but there are a lot of challenges there. And these are just some of the numerical method we use. For the state of charge study, we have not done as much. We're also starting. Again, the idea there is really we wanted to be robust against the user conditions. So we have got the typical user driving schedule from the Department of Transportation from US. So we do experiment, we run and try to develop different type of modeling so that will predict accurately. And we have some preliminary result. And the same way that we have equipment in our Shenzhen Research Institute where we could run experiment under different temperature, different conditions so that we could do much better modeling. So with that, then the last item, as I mentioned, I just wanted to use the remaining few minutes to introduce. This concept, the PHM concept, is not limited to just the system. It could be related to human health, okay? And I also have separated project in healthcare and public health. So that's how I relate them together. You could think of the human health itself is also a system, okay? When you are born, you are just like a fresh manufactured product, like a new manufactured vehicle, okay? Same way for a manufactured vehicle, if I collect all the data over the lifetime of this vehicle, I could predict much better about this individual vehicle, okay? Same thing before I manufacture a whole bunch of them, I could predict a population behavior. But once the car is bought by an individual, If I am able to follow the individual, the data of the individual, I could predict much more accurately. The same way for human health. This is called personalized medicine. The same thing they do genetic research, okay, for population, okay? But once you are born, even you have the same genes, if you don't take care of your health, you don't take care of your body, same gene could result in very different health condition when you get old, okay? Same way if I get all your human health record, I could do much more accurate modeling by following it. Of course, the human is a lot harder because there's a lot of privacy issue. They're all of security issue, okay? So that is harder to approach, but we are doing similar work there. So a lot of similar things we could do, but I will not get into the detail here. So with all that, I will just stop here, and thank you.
Thank you, Professor Gocui. Very nice talk. And our last speaker is Professor Li Wenrong. Professor Li is going to present the topic, Optically Induced Electrokinetics, a digital path to cancer cell manipulation, patterning, and differentiation. Professor Li is currently a chair professor of biomedical engineering in Department of Mechanical and Biomedical Engineering CityU. We're happy to have Professor Li join us 3 years ago from CityU. Actually, I started to know Professor Li's name 14 years ago, mainly because of his significant contribution in micro and nano system. Before Professor Li joined CityU in 1997 as a faculty member, he has a lot of industry experience in United States, right? So Professor Li, as we all know, Professor Li is very professionally active in IEEE Society. I give you some data, okay? Professor Li has been guest editors for several IEEE transactions, including Transaction on Automation Science and Engineering, IEEE ASME Transaction on Mechatronics, and IEEE Sensors journals. He was the founding editor-in-chief of the IEEE Nanotechnology magazine. This journal now has already become one of the top circulating publications in IEEE. Okay. And Professor Li has co-founded with his students 3 startup companies in Hong Kong as well as mainland China. And the company are very successful in commercializing the MEMS and nanosensor related products worldwide. Professor Li was IEEE Fellow, ASME Fellow. Very recently, let's congratulate Professor Li to be elected as the President-elect for IEEE Nanotechnology Council. That means from next year, he will be the formal president, all right? Okay, now let's welcome Professor Li for giving his talk.
Thank you very much, Professor Shundong. I'd like to take this opportunity to really thank Professor Gary Feng and Professor Shundong for, 3 years ago, allowing me to come from Chinese University to over here. I think CityU is definitely one of the most dynamic, upward-moving universities in the world, not just in Hong Kong, but in the world. Okay, so I'm very pleased to have the opportunity to work over here and collaborate with many great researchers over here at City University of Hong Kong. Get the PowerPoint up. Okay. This one. Thank you. Okay, thank you. Okay. In fact, many of you may be curious, about why Professor Sun Dong invited me to talk over here, because if you look at the title, it's nothing to do with manufacturing. But I think as I finish my talk, you'll realize that, like Professor Kwok just mentioned, that human body is actually a manufactured system. It's just a matter that we have no idea how to manufacture it at this point in time. But many of you may have read in the past few years that stem cell work in the area. People have used stem cells to create teeth, ears, nose, internal organs, and all kinds of different parts. The problem is that how do we actually direct the fate of stem cells? Okay, so you can think of it as what I'm doing is a way to isolate, to differentiate, eventually build, assemble stem cells or other type of cells to manufacture in certain parts for medical studies. So that's really the motivation of what I'm doing today, what I'm going to talk about today. I would first thank the students that worked on this the project I'll mention today, the results. I was very fortunate. I had a chance to work with students from 3 different universities, I should say institutes. City University, of course, Chinese University when I first came to Hong Kong back in 1997. I worked there for about 13 to 14 years. Also from the Shenyang Institute of Technology, Institute of Automation, that is. For the Chinese Academy of Sciences, and they're very hardworking students, so I would like to thank them too for contributing to these results I'll talk about today. So, as engineers, we first want to ask, why manipulate, assemble, and differentiate cells? The easy answer is that there are a lot of, there's no standard technique right now for the medical scientist to actually separate, manipulate, and differentiate cells easily. Okay? I mean, there are systems available in the hospitals and also in research laboratories that they purchase that they're very expensive. But the reason why I got into this field is that my friends from, Chinese University, medical science researchers over there, they told me that they do not trust those systems. And also, they're too expensive for most labs to acquire. And that's why it's still a chance for engineers to contribute in this area. Now, just give you an example. I told you that stem cell cancer biology. Right now in the US, the NIH has a big initiative on trying to build 3-dimensional cancer cell tissues, meaning tumors. For example, if you talk to a medical doctor, they don't care what technology you use. They don't care if engineers do anything, okay? They just want to be able to take your device, go to the hospital and test it as fast as possible and get the results as easily as possible. So none of these medical doctors, they do not look at the research value of engineers and medical scientists as very important. Because if they would say, why should I test your device? You think when it works on a 2D surface, for example, cells, in one layer of cells, they will not work in real life. Real life means us in a hospital, sick. They want to find out what's wrong with us as soon as possible, okay? So a big initiative in the US, like I mentioned, they want to build 3D cell structures, like a tumor, so that could allow medical scientists to do, extensive studies on them. Why cancer? In fact, most of us will die of either cancer or heart attack when we get older, okay? But the good thing is that you're probably less likely to die of some cancer than car accidents, okay? Car accidents actually are one of the highest killers. This is in the developed world. If you're from, let's say, this developed parts of the world, like, some parts of Africa, some parts of India, you're more likely to die of AIDS or infectious disease, okay? Like the Ebola that we see these days, bacterial disease virus. Now, in Hong Kong, most of the people will not think that the skin cancer is a major problem. In fact, most Chinese think that we do not get skin cancer because most of the skin cancer cases you see are from European or American friends, Caucasian colleagues. Now, but let me make it clear over here. In fact, in the U.S., 50% of all cancers found are related to skin cancer, okay? But of these, around 2 million cases of cancer found each year, only about 75,000 are considered eventually malignant, meaning that it's deadly, okay, or cause danger to your life. In fact, around 2 million cases found, only around 12,000 patients actually die in the U.S. each year. In Hong Kong, you're very lucky, okay? I should say we're very lucky. We're 100 times less likely or less common to catch skin cancer than Australians. Okay, so I'm sorry to say, Gary and Professor you guys more likely. Okay, in the U.S., we're 3 times less likely in UK. However, something that the Chinese always say, okay, you get skin cancer because you expose yourself too much in the sun, but that's not the case. This is according to the Hong Kong Cancer Society data published 2 years ago. Actually, Hong Kong people catch cancer later stage in their life, skin cancer that is. When they catch it, it's much worse than our Caucasian friends, okay? In most cases, this cancer are in non-sun exposed areas. So even if you don't go to the sun all your life, you're still going to catch skin cancer. That's a message that, to our Hong Kong people, okay? So we have to worry about it. It's a problem, eventually, for all of us. So to just give you an example of why do we want to separate cancer cells, let's talk about skin cancer. Turns out there are 2 types of skin cells. Major types is keratinocytes and also melanocytes. Melanoma, is a term for deadly skin cancer. Okay, if you catch that, you're most likely going to die, and it will be one of the 12,000 each year in the U.S. The reason why I use the U.S. data is because I think that's the country that uses the most systematic way of collecting data. In fact, I could not find any data from China systematically. Hong Kong is starting to collect this data, okay? So eventually I'll have more detailed Hong Kong data for this disease. Now, my colleagues in the medical science area, they told me that it's actually very difficult, even using a $1 million Hong Kong piece of machine to separate this. The success rate is only 5%, okay? And this is one of the major motivations for the research. And there's something called the FACS, or fluorescence activated cancer cell sorter, okay? This is a very standard equipment in the research labs and hospitals. They don't like it because you have to put some type of fluorescence particle inside the cells, and they think that might have some poisonous effect to the cells eventually. And then, when you try to study cells, you want them to be as natural as possible. So by putting some particles inside, they would think that it's not, whatever effect that they observe may not be real in a human body eventually, okay? So that's one of the things that they do not want to deal with. And so our hypothesis is very simple. In nature, there are 4 forces, right? Gravitational force, electromagnetic force, also the strong and weak intermolecular force. For example, how do I distinguish humans? If I take 2 people, push you off ICC, the tallest building in Hong Kong, right? How do I distinguish you? You have the same gravitational acceleration, but one with bigger mass is going to fall faster, provided that the same posture, same cross-sectional area, okay? So mass is one factor. And also the cross-sectional area, like I said, if you could spread your body wider, you're going to fall slower because of the drag force due to air friction. Therefore, you could think of this. Can we look at cells having distinctive properties, either electrically or mechanically, if we apply some electric field to it and then watch its motion and see what happens? Okay. And I'll show you that there are a lot of interesting things that we have found. Just to define electrokinetic force, this is actually not a new term. This is a term that's been used by chemists for many years. The 4 major ones are electrophoresis, dielectrophoresis, which we call DEP, electroosmosis, and electrothermal flows. I will not explain these, but I wanted to point out that DEP is something that a lot of researchers in medical science and also in engineering are using right now, because this is a dominant force. The thing I'd like to point out is that DEP force depends on several factors. For example, the electric field applied between a particle, okay, between the electrode of the particle, and also the geometry of the particle, also the conductivity of the particle in the medium. This is a video showing you that you have 2 electrodes. You apply electric field between them, and this is some nanotubes in a ferritic medium. You can actually attract the nano entities very fast, very quickly, between the micro gaps, okay? So this DEP force in a big macro scale world, we do not feel it. But in the micro nanoscale world, it's actually a very dominant force. It works on cells, because most cells are between around 1 to 10 microns, 20 microns. So we consider them as micro scale. DNAs, molecules are considered nanoscale, okay? So you can see that why DEP is very, very prevalent in terms of research is because that they apply to both micro and nanoscale worlds, and they work very effectively. So I just mentioned that DEP force depends on frequency, right? So, and there are so many different phenomena. When you apply DEP, the key is that you have to select the right frequency bandwidth and the right magnitude, the right medium, also the right, excuse me, the right materials in order to activate enough DEP force on cells and DNAs. Let's look at a cell, for example. Every single cell has, we could define them clearly by 2 boundaries. One is called the membrane. Okay, we have a cell membrane that surrounds the cell. Inside the cell, there's fluid, also other parts of the mitochondria, nucleus, and so forth. Also the fluids inside. So in terms of electrical properties, we like to clearly define that there are 2 different electrical properties. For example, the conductivity and permittivity of the cell membrane, and also the conductivity and permittivity of the internal parts of the cell. We call it the cytoplasm, collectively. So based on this fact, our premise is this, okay? We want to be able to digitally, meaning that programmably, control the electric field around the cell. We activate the field at will and see what happens to the cell. Will they go up and down? Will they vibrate? Will they rotate? Will they, accelerate? And how do we do the electric field? Let me just briefly explain that. For example, we have a microfarad channel. Okay, this is by microfarad, this means that it's in terms of microns. For example, your hair diameter is about 100 microns. So this is the scale of dimension that we're talking about. If we put on the surface of a microfarad chip a special material, we call that the optoelectronic material, meaning that if you shine light on a certain parts of the material, it becomes conductive. If the material is not exposed to light, then it's just like an insulator. It does not conduct electricity. So as you imagine, if I project a certain image onto a substrate, and I project a ring, for example, I could create an electric field locally around 3 cells, and I could create an electric field cage that traps the cell, okay? This is a basic concept. Let me show you a video to illustrate this. This is an actual video taken under the microscope, and you can see that I use a program to control the electric field, and these are microbeads around 10 microns in size. And the yellow sphere represents electric field force. So I could actually manipulate this DEP force, as I mentioned, to manipulate, to dissect, to move around micro-scale entities as well. And I mentioned earlier that DEP force depends on the geometry and properties. For example, 2 different sizes of cells, they have different geometry. Okay? So I could apply one single DEP force, but they would act on the different particles differently. Just like gravitational force act on humans with different mass differently. Okay? You can see that I could separate 2 different size particles very fast. Now, while doing this research, we found something very interesting that was unexpected. For example, I'm not sure if you can see clearly that this is a Rudge cell, cancer cell, and it rotates under a non-rotating electric field. Imagine, electric motor has been around for a while, right? And we make motors spin by putting electrodes at different positions, and we, activate different phase, apply different phase currents to make the motors rotate. But in this case, if I put a cell in a fixed electric field, the cells actually rotate. So the question is, why is that? Number one. Number two is, if we can distinguish why, this spins, can we use this principle to actually differentiate different types of cells? For example, the cancer cells and healthy cells have different spin rates or different frequencies at which they will spin, faster. For example, the peak frequency, resonant frequency. Now, there are 2 hypotheses. Like I said earlier, one is that the spin could be due to the electrical property of the cells, or also some cells have what they call, they digest something called melanin, or artificial bioparticles inside, or they produce them inside. So there is some mechanical imbalance, mass imbalance inside the cells that could cause the rotation, okay? And sure enough, we've done a lot of studies on different cells. Again, this is a collaboration with Chinese University and also University in Beijing, a hospital in Beijing rather. In this case, we had white blood cells, cancer cells, normal healthy cells. We want to see what happens to the spin rate just by applying a fixed electric field. Remember, like I said earlier, the red area you see is the optoelectronic material. Where we shine a light, that's where the electric field becomes stronger, it becomes conductive. The red areas are not conductive. And sure enough that, we collected data on rotation rate versus applied voltage peak, and also applied frequency. And each type of cell do have their distinctive rotation peak frequency, and also how they respond to voltage is very different. And this is just give you a simple table chart illustrating the effect. Lung cells, skin cells, these are healthy cells, that is. They have no pigment. That means that they have no melanin inside, or no bioparticles inside, and they do not rotate. Really means that they have to be kind of weird-shaped geometry for them to rotate, some kind of mass imbalance. But for melanin cell and also B16 cancer cells, they do rotate 100% of the time. Okay, so it proves our basic conjecture that if cells have particles inside, they'll rotate. However, that still does not answer the question. They rotate due to mass distribution imbalance, or because the particle induces a certain electrical property that causes the cells rotate. We still have not answered the question yet. But I can tell you that we're trying to do a simple experiment. We got some white blood cells from mouse. And that white blood cells, they exist to attack invading bacteria inside your body, right? So they could eat up a lot of things. So white blood, these specific type of white blood cell microphage, they do not have melanin inside, okay? So our basic example is that, basic test is that we want to make it digest artificial melanin and also latex beads, micro beads inside, and then see if they rotate. And sure enough, You can see in this picture that they rotate. Okay, remember, without the pigments, the original macrophage will not rotate. But once you begin to digest the beads and also the artificial melanin, they start to rotate. Also, they rotate at different axes, right? So that tells us that, again, we have not clearly answered the question, whether the mass imbalance or electrical property causes rotation. So the answer is still to be found, okay, at this point in time. This is our latest research we published about 6 months ago. But I'd like to mention that the short summary from the first part of my talk is this. We can use, we call OEK, optically induced dielectrophoresis, to actually manipulate position and then identify. And if identify means that we could actually make it rotate at different rates, so we know what type of cell this is. Okay? As you can see this video, depending on where you put the electric field, cell would react differently. Now, we also found something very interesting, and this is, we have matched with other people's results using other techniques, of course, is that red blood cells, they tend to couple together under this electric field. And also, we found out that if you're a sick patient, for some reason, the red blood cell do not couple and do not rotate, okay? And we found that some of the researchers have stated that if you're sick, your red blood cells actually lose its mass, and its shape would also change. And that, that I think coincides with our theory that DEP force act on these different entities differently. So we're going to try to use this as a way to diagnose healthy patients or determine them from unhealthy patients eventually. And I'll share the video, if this plays over here. Again, this is a video showing that red blood cells with cancer cells. And it shows you how fast we could separate red blood cells from cancer cells. In this case, the spherical cells are cancer cells, and the disc-like cells are blood cells. Okay? You can see that we could, by one sweep, they're separated and aligned. Sorry. I'd like to, reinforce the fact that engineering is actually very, very important in this kind of research. You see the cell rotating. How can you actually use your eyes to take the data? And how do you determine which axis is rotating? Okay? And then you have to collect data for so many cells. You cannot just, get your data from just one cell. Biologists will never trust you, excuse me, and they can never publish your data or your paper in a good journal that way. Okay? So my students and my collaborators here at CityU worked on some algorithm that automatically determines the rotation rate. I can say that my students at CUHK used to take around 1 week just to take one single data. Now my students at CityU could do, few minutes of work. They'll give you an entire chart of maybe 10 cell data. So this is a very good advancement by the work here at City University. Again, so the whole goal is how to merge engineering techniques with, for biologists to improve their research techniques. So now we're working on something called automated computer vision-based differentiation of cells. And again, you put a cell in an electric field, in a ferritic medium, you have no idea how it's going to rotate based on your eye test. Okay? It's very hard because they could be rotating up to 100 RPMs per minute. It's impossible for our eyes to pick out the rate. So computer vision is very important. Give you an example. Like I said, if I push you off a building, I could tell you, if I could measure your speed of falling, okay? I could actually tell you what your mass is if I know the gravitational constant. Now for cells, imagine this. If I have a cell resting on the bottom of a microfluidic surface, and I impart a very small DEP force, make it jump up, okay? After it jumps up and I turn off the DEP force, then I let the force of balance take over. So if you look at the physics, you have the gravitational force pulling down the cells. At the same time, the viscosity force, or the frictional force of the fluid, is trying to counter its motion downward. Also, there's a buoyancy force. If you go through the derivation, you'll find that the density of the cell can be related to the density of the ferritic medium and also the velocity of the cells by this equation, simple equation. So this tells us that if you can measure the cell motion precisely, it actually tells the cell density and mass, okay, eventually. And sure enough, we have used computer vision to determine the cell falling state, and from there we calculate the velocity and able to determine that mass for each cells. which is very comparable to conventional techniques, except conventionally you need to take hours to determine not one, but what do you call it, population properties. We're the first in the world to report a single cell mass density determination within 5 seconds, okay? Imagine, project a light, cells move up, we take computer images, and we analyze it to get you the density and mass all within 5 seconds. Another example, if I could impart a certain electric field, in this case just a straight line, so that the cells accelerate because of the small push of the dp force, and I could track his acceleration profile, position profile, then I could determine its time constant, okay? Because eventually the cell has to come to stop due to the balance of forces. Sure enough, for red blood cells and cancer cells, they have two very distinctive, what we call transient motion profiles. Using support vector machine techniques, this is a statistical analysis, we can clearly separate two kinds of cells, okay? So imagine this, eventually I just have to put a light image on a cell, measure its trajectory profile, I can classify it into different categories of cells. Now, let me take about 10 more minutes about, besides manipulating cells, we could actually manipulate all kinds of different structures using DP. I mentioned earlier, there are 4 fundamental forces in nature, right? And weak and strong molecular force is something that we do not try to deal with, except, chemists. The strong strong molecular force is something like, let's say, something that holds this table together. Molecules are bind together, okay? Weak is more like, let's say, your interface force. It's not a strong binding force. And it turns out that this binding force is related to electric field. For example, if I put a polymer solution in a microfaradic system, apply localized electric field, I can actually create solid polymers immediately, okay? This is a faradic solution, and I shine an image of the Chinese flag. It's almost October 1st, so we need to be patriotic to show this. And you can see that becomes a polymer structure. What's the usefulness of this polymer structure? Now imagine this is a hydrogel, which is a gel that people use now to grow cells and allow them to live for a long time. We can actually put cells inside polymer solutions, and we shine light specifically at the cells. Then we would fix it. Okay? We can actually fix it right there and to avoid studies afterwards for cell injection, cell testing, and so forth afterwards. Excuse me. Another example is that we could use these polymer structures to pattern cancer cells. And these are nice pictures, but what's the application? We found that actually cells, they react to the environment, even cancer cells. Okay, so if you squeeze them, they tend to grow a certain, kind of like conservation of mass, for example, but in cells in case, I think it's conservation of volume. They tend to elongate themselves or shorten themselves or flatten themselves just to fit in a certain space. It turns out that last year, researchers from UC Berkeley, they found that you could actually reverse the fate of cancer cells. What does that mean? We know that cancer cell is really, the basic concept is that a healthy cell somehow gone wrong in its development, division. And it becomes cancerous, becomes bad cells, and it tends to divide even faster after that. However, no one has ever proved that it could give it drugs and let it reverse. They become healthy cells again. It turns out that Berkeley researchers found that if you apply some mechanical stress on these cancer cells, you can actually reverse its fate, meaning from cancers back to healthy cells. This is a very important study, okay? It shows you that maybe the Chinese are correct. Some illness could be massaged and cured by Chinese medicine and Chinese techniques. This is fundamentally very, drastic, I think. Western medicine has been around for so long, and they've been trying to cure cancer cells with poisonous medicine, for example, that will kill cancer cells at the same time attack healthy cells. But what they found, the reason is that if you actually apply the proper mechanical stress, you can reverse the fate of the cancer cells. Okay? So this is something that we're trying to investigate. We found for sure cancer cells do respond to mechanical forces very, very rapidly. Okay? So something that has some scientific value. Let me give another example. One of the problems with some of nanotechnology by name, because we could see nanoscale entities now, right? before nanotechnology came about, people have been working on surface science, working on material science for a long time, in chemistry a long time. But many of these scientists have started calling themselves nanotechnologists. Why? Because they could use AFM, atomic force microscope, to observe nanoscale entities. But there's still a fundamental limit. You're not really seeing, when you use AFM, you're actually feeling the force when you scan a certain entity over. So we're trying to develop a technology now using, we fabricate some microlens to see below 100 nanometer entities optically. We're trying to go beyond the optical limit. And this is doable by controlling, again, DP force to create interfacial instabilities, to create structures. But of course, we try to overcome the instability and try to make something more controllable. SIA, Shenyang Institute of Automation, this is done by my students in China. We can just show you, for example, that we could make arrays of mirrors. The mirrors can be controlled by the time you apply the DP force. Also, the focal length and diameter can be controlled. Okay. This is the last slide. I think Professor Dong wants me to finish it as soon as possible. So let me show you that besides fabricating micro mirrors, we can actually fabricate nanowires in the microfarad channel at room temperature. Okay, you can see that wires are growing out of this DEP force field. Okay, and you can see that this is the eventual wire you see. Why is this significant? This means that eventually we could actually fix cells and then grow nanowires into the cells and try to read the cell signals eventually. Okay, this is something that we want to work on. Now, to conclude, I hope I have convinced you that OEK, optically induced electrokinetics, or optoelectrokinetics for short, is an advanced manufacturing technology, because I've shown you many examples how we can manipulate, assemble cells. Also, we could produce polymers, even including micro nano lenses, also nanowires. Okay, these are very advanced techniques for the future. And these are the details that I just said, polymers, and eventually we can integrate all these techniques into nanosensors, even sensing biological entities. Thank you very much.